In this video, we'll talk about what concave up and concave down means and how it connects to average rate of change. So concave up, you think of it as like a cup. It can hold some water. But this entire function is concave up. And concave down is down, they say like a frown, so you remember which one is which. So now I want to connect the increasing, decreasing part of it. So if I think about cutting this graph in half, this side is decreasing and this side is increasing. And similarly, do something here. This side is increasing and this side is decreasing. So the first half of this concave up graph is decreasing and concave up. The second half is concave up and increasing. On this concave down function, the first half is concave down increasing, the second half is concave down decreasing. And we'll talk more about that, but I first want to look at an example in GeoGebra. So let me open a new window, make it big. I'm going to change the font size so it's easier for you guys to see. I'm going to put in the function f of x equals 0.5 times x minus 4 quantity squared plus 2. Then move that around, make that wider. Okay, so here we have a concave up graph, and I want to look to see what's going to happen with the rates of change. So I'm going to first put on a bunch of points. So put a point there, A, B, C, D, F. Alright, and then I'm going to put segments. So instead of lines, I'm going to put a segment. So I'm going to say segment, and I'm going to do A comma B, and that's going to draw a line segment between A and B. And then segment B comma C, and segment C comma D, and segment D comma E. So I've created line segments between A and B, B and C, C, D, and D, E. And I want to look at the rate of change, or the slope, of those lines. So I'm going to do slope of A, little a, because that's the first segment. Then the slope of B, slope of C, slope of D. Okay, so what's going on here? We have negative 2.95, then negative 1.22, so it's gotten bigger. And then the next slope is 1.23, so now it's changing to positive and getting bigger. So notice that the slopes are increasing. Alright, so let's go back to here and write down. So concave up, we know, let's use a different color. Slopes, or average rates of change, are increasing. Alright, so we can probably guess that with concave down, the slopes should be decreasing. Let's check it out. So I am going to just change my functions to be negative, so it's concave down. And I'm going to change that to be plus 6. Alright, so I just changed my function, but I have all the line segments already in there. So notice my slope is starting out at 2.95, then 1.22, then negative 1.23, and then negative 2.98. So my slopes start out positive and get smaller and then more negative, so they are decreasing. Alright, so here, slopes, or average rates of change, are decreasing. So I'm going to summarize some more. If I just look at, I'm going to draw just this. That function is decreasing at an increasing rate. And then this part, again, it's concave up, but it's increasing, so this is increasing at an increasing rate. And so do some similar stuff on this one. So that is concave down and increasing. So it's increasing, but because it's concave down, it's increasing at a decreasing rate. And this one is decreasing at a decreasing rate. Here's an example that we looked at last time about the number of women in the United States employed outside the home. In 1970, there were 31.5 million women employed outside the home. So we answered questions about this, and we looked at average rate of change. So if we made an average rate of change chart, so here we have from 1970 to 1980, the average rate of change is 1.4 million women per year. So on average, between 1970 and 1980, 1.4 million more women worked outside of the home per year. So based on what we learned about concavity and the rates of change increasing and decreasing, and based on this average rate of change chart, we want to describe the behavior of the function W of D, so the number of women working outside the home. So notice that the average rate of change is 1.4, then it goes to 1.13, then to 0.95. So those numbers are getting smaller, so the average rates of change are decreasing. So what does that mean about the concavity? The concavity is, which means the function is concave down. Then we go back to the original function. Our initial values are increasing, so the function is increasing at a decreasing rate. So W of D is increasing at a decreasing rate. And so if I had to sketch a graph of that, it's increasing and concave down. It looks something like that. In this last example, you have a graph and you're asked lots of questions about it. So here's my graph of f of x. And we're just going to look from 0 to 10. So think of this as being the cutoff. And I want to know, where is f of x increasing? So it's going up, 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 up until about right here. And then it goes down to about right there, and then increasing again to about right here, and then decreasing. So how do we write that? So we say it's increasing on the interval from 0 to, let's say this is at 2.2, and we'll say this is at 4.3, this is at 8.1, so it's increasing from 0 to 2.2, and it's increasing, so union, increasing from 4.3 to 8.1. And then where is it decreasing is in the other spot, so from 2.2 to 4.3, union 8.1 to 10. Next question is, where does it have a maximum? So if it just asks where, that's asking what x value does it have a maximum at. So we can see there's a maximum at 2.2 and at x equals 8.1. So maybe I should talk a little about what it means to be a maximum. So this point is the largest one in my little circle I drew. So there's a maximum in that region. This is also the biggest around. If it asked for the global max, so the global max would be the biggest point on there. So that would be at x equals 8.1. But this is considered at 2.2, it's considered a local max. So usually if it asks where does it have a maximum, you'd say all the places there are maximums. Then it said, what is the maximum value? So the values, so the one that corresponds to 2.2, the maximum here is at about 3.4 maybe. And the maximum value at 8.1 is at 6, so the y value is 6. Then where are the inflection points? I haven't told you what inflection points are yet. Inflection points are where concavity changes. So inflection point is where concavity changes. So maybe let's answer F and G first, and then we'll do the inflection points. So where is f of x concave up? So this is concave down, concave down, concave down, concave down, concave down until about right here. And then concave up until somewhere in here. And then concave down. It might change again somewhere in there, but so concave up, like I said, you should label these points. This point is about 3.2. This one is at 6. So where is it concave up? Is concave up between 3.2 and 6. And then it's concave down the other areas. So 0 to 3.2 and 6 to 10. So if an inflection point, and looking at E again, the inflection point is where the concavity changes. We see the concavity changes at 3.2 and at 6. So at x equals 3.2 and at x equals 6. So in this video we talked about the connection between concavity, or what it means to be concave up, what it means to be concave down, and the relationship to the the slopes. So the slopes, or the average rate of change, are increasing if the function's concave up, and the average rate of changes are decreasing if it's concave down.